Okay, so we were studying rectifier control of, chopper control of separately excited DC motor. Okay. I think yesterday we had seen motoring as well as regenerative braking. Also how to obtain simultaneous motoring and regenerative braking simply by changing the value of the duty cycle. Okay. The last topic that remains is dynamic braking. Okay. How can you use a chopper for dynamic braking? We all know that in case of dynamic braking, the field is kept connected to the supply, whereas the armature is disconnected from the supply, and a resistor, a rheostat, is connected across the armature terminals. The motor starts acting like a generator, and the energy is dissipated in the braking resistance. So the question is, how can you use a chopper now when there is no supply?
Sir, in absence of supply, sir, how, sir?
That is the question. How will you use a chopper here when there is no supply? Okay. So under normal conditions, see the armature resistance, inductance, back EMF, RA,
So we can use it in back. Means when the chopper is off that period.
This is your braking resistor connected across the armature terminals. This is the armature voltage VA, and this is the armature current IA. Okay. Flowing because of the back EMF through the braking resistance, RB. Okay. You have the field winding here, and that is connected to the DC supply, fixed DC supply. So, how can you use a chopper here? You have not studied this before? Nobody?
Sir, not in that much, sir, intensities.
Okay. So basically, the chopper will be connected across the braking resistance. Okay. This is your TR now. The purpose of the chopper now is not to regulate the supply, but to regulate the value of the braking resistance. Okay. Your TR will control the effective value of braking resistance as seen by the armature circuit of the motor. Okay. It will control the magnitude of the energy that is dissipated in the braking resistance and hence its effective value. Okay. If we draw the waveforms of VA and IA, okay, let us say this is the on time, this is the off time. T on, total time T. Okay. So when the chopper is on, what will happen? How will the current flow? Current will flow from back EMF, armature inductance, resistance, TR, and back to E. Okay. No current will flow through the braking resistance, RB. Correct? Yes.
Yes, sir.
So what is the value of the armature voltage?
0.
Sir, E minus IRA.
E minus IRA minus LA DIA by dt, that is equal to 0.
Yes, sir.
है ना? For the other side, the armature terminals
Yes,
are
sir.
short circuited. ठीक है? So that is 0. What will happen to the armature current? Will it increase or decrease? Will it increase or decrease?
So it will decrease, sir.
Armature current,
Yes, sir.
yeah, it will increase because the armature terminals are short circuited. And we are drawing the steady state waveform. Okay. So the armature terminals are short circuited. So because of E, there is no there is no opposition here. What was there before 0? Before 0, RB was there. And the chopper was off, so
Yes,
RB
sir.
was there.
Then,
Now you removed
yes, sir.
RB and connected a short circuit. So the armature current will increase. Okay. Now at this instant, you turn off the transistor or the chopper. So as soon as you turn off, the chopper, the current that was flowing earlier like this will now have to flow through the braking resistance RB. Okay. Because of which earlier there was a short circuit, now there is opposition to the flow of current, so your current will start decreasing. Again you turn on the chopper and the current increases. Okay. What will happen to the
Sir,
voltage? Yes.
sir, it is not increasing, decreasing suddenly because of, sir, inductor, sir.
Yes.
And sir, we assume that the loss across the inductor is 0. Sir, in this case, sir, we have to assume it, sir, it is happening.
We assume that the what?
Loss across the inductor, sir.
Loss across the inductor. No, we are still assuming that it is 0. The inductor is lossless.
Sir, in practical inductors, sir, those are lossy, sir.
So you can assume that the lossy part of the inductance is included in the resistance. Okay.
Okay, sir, got it.
Okay. What will happen to the voltage? What will happen to the voltage? VA. Now VA will be equal to E minus LA DIA by dt minus RAIA minus RBIA. Is that correct?
Yes, sir.
It will not be equal to 0 now. Okay. And if we are assuming that E is constant throughout this period, for this small time duration, the chopper of time, which is very, very small, okay, in the range of milliseconds or microseconds. So if we assume that E is constant during this period, then okay, as the current decreases, this armature voltage VA, okay, what we can see on this side, if we find out VA from this side, it is E minus LA DIA by dt minus RAIA. Or if we find it from this side, this VA is simply equal to RB into IA. Correct? So as IA is decreasing, RB into IA will also decrease. Okay?
Sir, but if we see from the back EMF side, sir, it should increase, sir.
No, it will not increase.
Sir, due to inductor, sir.
Because of inductance.
Okay, sir.
See, there are two sides to this. This VA is equal to RB into IA, or it is also equal to E minus LADIA by dt minus RA into IA. Okay. So as per this, as IA is decreasing, RB into IA will also decrease. As per this, even if we assume that E is constant, this is decreasing. Then to balance
And
this,
LA by DP
this
is
has to increase. Okay. Once again, the chopper turns off. Sorry, the chopper turns on, so your voltage again falls to 0. Okay, is this clear, everyone?
Yes, sir.
Now, if you assume for the time being that the armature current is constant, there are no ripples in the armature current, then what is the energy consumed by RB, energy consumed by the braking resistance during a cycle of chopper operation? How much energy will be consumed? Energy consumed by RB, that will be equal to IA square into RB
RT.
multiplied by T minus T on.
Yes.
Right?
Yes, sir.
Because current is flowing through the braking resistance for the duration T minus T on. 0 to T on, the chopper is on, no current flows through RB. This duration, that is T minus T on, current flows through RB. So energy stored or energy consumed, not stored, it is a resistor. Energy consumed by RB during a cycle of chopper operation is IA square RB multiplied by T minus T on. Okay? So the average power consumed by RB, average power will be equal to the energy consumed over a cycle divided by the cycle time. Okay. So that becomes IA square RB multiplied by 1 minus T on by T. Okay. Now there is no supply here. So our earlier definition that duty cycle is time for which motor is connected across the supply divided by the total time. That definition cannot be applied here. So we assume that now the duty cycle is simply T on by T. Okay. So average power consumed by RB becomes IA square RB multiplied by 1 minus del, where del is equal to T on by T. So the effective value of RB, that will be equal to average power consumed by RB divided by IA square. So that will be equal to RB multiplied by 1 minus del. Okay. So this is the effective value of the braking resistance. We can control the effective value of the braking resistance as seen by the armature by changing the value of del. Okay. If del is equal to 0, that means T on is equal to 0. That means your transistor is not turning on. Then RB effective will be equal to RB. Okay. Because your RB is continuously connected. If del is equal to
Sir, it is denoting that RB into 1 minus del amount of resistance will always be there.
Yes.
Okay, sir.
Okay, so if del is equal to 0, then RB effective will be equal to RB. Because your transistor is never turning on. Okay? And if del is equal to 1, that means T on is equal to T. Del is equal to 1. So your transistor is always on. So your RB effective will be equal to 0. Okay. So by changing the value of del from 0 to 1 or from 1 to 0, you can control the effective resistance from 0 to RB. Okay. And hence you can control how much energy is being dissipated in the braking resistance, and you can control the dynamic braking. Basically, you can control the time for braking and all those things. Okay. If you remember, if we don't have chopper, then we use 2 or 3 braking sections of the braking resistor. Okay. Initially, when the braking starts, you connect the whole braking resistance, and as the braking progresses, you cut out the sections so as to maintain a high value of armature current so as to get faster braking. Okay. So here, instead of using a number of sections, you can simply use a transistor, okay, and you can control RBE without having to cut out sections. Plus, you can get any value of RBE that you want between 0 to RB. Okay. Okay. Did Sumit come? Sumit has joined. Sumit and Priya Malhotra? No? Take any questions here? Anyone? Suman? No, Sumit.
So sound was not coming, sir. Please, sir. Repeat.
I was asking, are there any questions?